Hi everybody, I'm Harry, and I've pressed the wrong button. There we go. I'm Harry, and I work at Oasis Protocol, and I think today we're going to play buzzword bingo. So like faster, multi-chain, account abstraction, and beyond ZK. So that was a bit of a late night decision thinking up this one. But anyway, I think for a bit of perspective and a slice of history, like the early ARPANET in the 1970s was dominated by mini computers, mostly from the DC and such as the PDP-11 there. And in the late 1960s, the most powerful IBM mainframe could have 16 million instructions per second. And at the moment, we're not counting instructions, we're counting gas. And most of the L1s are running in the sort of 1 megahertz to 15 megahertz range. And yeah, we're sort of, if we look at the early evolution of the internet and compare it to what we have now, I think there are lots of similarities. And if we have that in mind, well, how's that relate to blockchains? Well, at the root of it, we're mainly concerned about sort of transactions and finality. And if everybody in the world uses like a single chain, then life and finality is much simpler. But as soon as we start adding a second chain, to scale up or just to do it a bit better than the other chains, then we need to start thinking about finality again. And to get a sort of a consistent linear state across all of the chains, we have to consider, say, what happens if on one chain we depend on the finality of another, such as a cross-chain swap, and if either of the chains rolls back or suffers from a reorganization or a 51% attack, then somebody's going to lose money, or the contracts on either side sort of may end up out of sync, and we might even break stuff forever, which is not good. So even if we had like a bigger mega chain of chains and like my big finality Pac-Man there, things can still all break in sort of weird and wonderful ways. And you can see that once we start looking at like the big graph of cross-chain transactions, so any large system will inevitably be in a constant state of failure, but only small parts of it will be failing, and hopefully not everything depends on everything else. So if you want to design like a really brittle and fragile system, it's actually really easy. So you just make it depend on the state of a handful of different blockchains all at once, and that means that if any of the chains stop working, that's okay. We can just wait until the single point of failure stops failing. This is like especially a problem with message passing bridges, where if your contract's designed so each message between a pair of chains has like a sequence counter, to make sure you can't replay old messages. That means that the messages must be delivered in order, and if one message gets stuck, it causes a roadblock. So by trying to enforce like serialization and linearity on the communication channels, you also introduced like an implicit dependency of everything that's already happened onto every future message that goes through that channel. So basically, you're slowing everything down to try and force a usually unnecessary sort of global linear order. And if the sequence is enforced on a per bridge level, then your messages will depend on every previous message going through that bridge. If it's at a per contract level, then it'll only depend on messages for your contract on that bridge. And the more granular you get, the more resilient to failure it will be. So subsequently, the more parallel and concurrent it can be, the more sort of failure resistance you get. So if you're thinking about adding like a sequence number somewhere, maybe you can reconsider like what the real dependencies are for each of the states, and what are the conditions for the state transitions. So a lot of time, we can turn a sequence into a hash chain where everything could end up being sort of idempotent and ordered based on the real dependencies, which makes it more resilient. And it's not that these are sort of bad decisions or sort of unnecessary complexity. It's just like the baggage that comes with building distributed systems. But anyway, so a slight tangent. But so why do we need account abstraction? Well, A lot of it comes down to putting band-aids on stuff. And again, they're not really poor decisions. It's just like a lack of foresight, and it's unavoidable. So if you combine that with like the necessity of being compatible with pretty much everything that's already been built, you end up where we are today. So what kind of problems am I talking about? Well, first you need to pay gas for transactions. For example, if you're on Ethereum and you want to interact with a dApp on Arbitrum, you send some dollars over the bridge, and you wait for finality, however long or short that'll be. And then you maybe add Arbitrum to your DeFi wallet, and after a handful of minutes, if you're lucky, your dollars are there, which is great. But I can't do anything yet because I don't have gas over there. And if I had some forethought, I wouldn't have sent all my dollars over there, because now I have nothing to convert to gas and then pay gas to bridge the gas. So first you convert a little bit, send that over, and then you can send the rest of the money and start clicking the DeFi buttons and have fun. But it doesn't really matter if you use a centralized exchange or an instant swap site or a decentralized bridge. It's all kind of the same problem. And like from my perspective, this sucks from a UX perspective. So the problem is that it gets worse. Like you then realize you've got the wrong kind of money. The dApp takes one flavor of dollar and you have a different flavor. So you hurriedly Google for a DEX. You click on the first link that shows up. You spend more gas for an approval. If you're lucky, it wasn't a scam. So everything I've sort of just been talking about is written in like the tiers of people who are new to the ecosystem. And they're like naive enough to think that it would be simple. Like account abstraction is a really vague term though. And it can mean almost anything. But if we're trying to narrow the scope down to something that's like more tangible, at the moment the proposed stack is the bundlers, the paymasters, the alternate mempool with like transaction predicates, and then smart contract wallets and 4337. And while these can work together to sort of make it easy to operate on a lot of different chains without doing this awkward gas shuffling, the major downside is it can make figuring out what your account addresses are kind of difficult, especially with the create to magic involved. And so all of this sort of solves a bunch of the problems I was talking about. But one of the missing pieces is transactionality, and more importantly, transactionality across chains. Because right now, like users largely end up operating on one chain, or they end up bridging from one chain to the other, either through centralized exchanges or bridges. And I don't think it's like abstract enough. So it breaks down the overall intent of the user into a series of sort of sometimes painful and error-prone steps. There we go. And why zero knowledge? So a few reasons. We're still discovering what ZK snarks and the sort of related ZK ecosystem can do. And while it's very expensive computationally to create the proofs, especially if you're doing things which can't take advantage of the underlying structure of the proof system, if we make gas calculus work out in our favor in a way which allows a significant reduction of the amortized costs over the protocol's lifetime, then it just makes sense to apply the ZK hammer to it, despite the added complexity. But one thing we can try to solve with ZK snarks is what has the biggest impact? Well, if we think about like Metcalfe's law, where the intrinsic value of a network is proportional to the square of the number of nodes, that means that the more communication overheads we can cut out while still being hyper-connected, especially if it's fairly trivial stuff like just replicating a little bit of state from one chain to the other. That means we can do cool things a little bit cheaper, and because there's less messaging involved, we can do it faster as well. And there are a couple of projects that are working towards this. A couple of people here today are working on this stuff. But generally, we've got ZK Bridge and Brevis and Polyhedra and a few others, where the sort of consensus algorithms themselves can be run inside a ZK circuit. So it's essentially a ZK Lite client. And in reality, that only works on some chains because ZK is hard, the consensus algorithms are complicated, and research takes time. But if we imagine a world where like every single ZK proof, you have a ZK proof of, a single ZK proof of the current finalized state of every chain at the same time, and every minute or so you publish that onto every chain. So now you can prove the state of any chain from any chain, And we've gone from like the n squared to just n, which is pretty cool. But so then I can start solving account abstraction problems without bridges, and I can have global transaction predicates which depend on the state of multiple chains at once. For example, I can prove that I paid for gas in some other currency on some other chain for transactions on these chains, and I can all do that with privacy as well, which it's also really cool. So with no more bridges, we're getting hyper-connected, and according to Metcalfe's law, we're attaining like the maximum network value without all the communication. But the problem is I don't think that's going to happen straight away. So we need to figure out how to build this and to make it production ready. And when it comes to like mass adoption, we've already got Visa contactless and Candy Crush is dominating. So that's instead of Web3 ZK. So I'm really trying with this buzzword bingo, but if we had this magic ZK every chain oracle, you're only going to be as fast as the slowest common denominator, which sort of varies from an hour to a few seconds, and the ideal is, well, it's instant. So if I give you a private key for a wallet, and there's already some money in the wallet, which has thousands of confirmations, and it's guaranteed that once I give the wallet to you, I won't have it anymore. Is that as close as we can get to instant finality? Where the only limiting factors are sort of how fast light travels through fiber optics and other processing delays, like copying from memory, writing to disk. And I think what I'm getting at is that if you're one step in a complicated multi-phase process, then like a few seconds is okay, it's not ideal, but 10 seconds, it quickly turns into minutes as you pass messages back and forth, because you have to wait for finality at each step, otherwise like CAP theorem starts breaking down, which is not good. And 15 minutes or an hour for each step, that's actually okay, as long as you're massively concurrent and operating in parallel. And you divided the work into the smallest possible chunks, and things like price variance over time is not a problem. But I think that this brings me on to confidential EVM and like why I'm this tool set that I'm trying to tackle these problems with, because it can do one thing that ZK can't do, which is confidential contracts can have their own secrets. And I'd like you to think about sort of how we could use this to solve some of these problems, which is like faster finality across multiple chains with enough abstraction that's like the difficult cross-chain interoperability stuff can be made to feel really easy. So what is confidential EVM? Well, basically it's just EVM, but the contracts have their own private state. And your call data is end-to-end encrypted between the contract and the DApp or the wallet, which means if your contract doesn't provide a method to access the state, then nobody can, not even the node operators, because in our case, we're using Intel SGX, which is a trusted execution environment to maintain that level of confidentiality. So all the contract states encrypted and only accessible by the contracts. And we get a few things basically for free, like MEV resistance and privacy, and like other people are working on these problems and they think they're hard, but it's not that difficult when you have the end-to-end encryption and private state, and you don't need to rewrite everything. It's just solidity. And of course, in our case, we've built built-in cryptographically secure RNG for key generation and passwords and loads of stuff, and a few precompiles for sort of hashing, signing, verification, and encryption and decryption. Because it turns out that without the precompiles for all of these things, it's not as useful. And of course, it's just like Ethereum, view calls are free. And in a free view call, the contract can also access its own private state. And that opens up a lot of areas that are interesting. The most obvious thing that comes to mind when I think about confidential EVM is privacy, and yeah, it can do privacy. Although currently, like blockchain land's roughly split into like two factions, which is the privacy maximalists, and I'm not sure if I'd call them the transparency pragmatists, but everything's transparent for one reason or another. And in reality, like most of the world is somewhere in between, where we very legitimately need privacy. And for most transactions, we need privacy for most people, for most transactions. So when you give a contract control over what it keeps private and what it makes public, you can have a much finer-grained level of control that reflects the real world. For example, if you want the address and stamp on the envelope to be public, you want the content to be private. Well, with sort of privacy on Oasis, which is our Oasis Sapphire, which is our confidential EVM, you can even control who's allowed to see the content or parts of the content or for how long they're allowed to see the content for. But the really interesting stuff for me is when you have contracts which can generate key pairs like an Ethereum or a Bitcoin or Monero address, and because they're smart contracts, they're predictable, and this gives them almost full autonomy. Because the view calls are free, and you can do things like have a contract which gives you a pre-signed transaction. Like if you want to deploy a smart contract wallet, the factory contract could pay the gas for itself for the initial transaction without all the extra infrastructure for 4337 and relayers and bundlers and paymasters. And you can do that with a bit of access control. So if you give the contract a proof, such as an invite code or like a Gmail bearer token, then that could be enough for the contract to say, okay, I'll sign the transaction for you. And with free view calls and access to confidential state, this sort of keeps leading in interesting directions. So the contract can encrypt data that only it can decrypt, or it can sign and verify stuff. And that's to make sure that it hasn't, you haven't tampered with the data that you're giving back to it. And we don't need to store this on chain, so we don't need to wait for this sort of consensus to mine a block and so on. Which means instead of a very complex proof-carrying data scheme, like we see in ZK worlds, you can just pass the contract, the encrypted or signed result from the previous invocation, and it can carry on with what it was doing. So basically, you end up with a rollup, but instead of a ZK rollup, it's a TEE rollup. And so whether you use view calls or transactions which modify state or a combination of both, the new way of looking at problems means you can take a lot of shortcuts, which you can also do with ZK, but some of them aren't possible or are quite difficult with ZK, because it can act as an honest third party, a trusted third party, which it can coordinate protocols for you, it can release transactions or release secrets or sign transactions, and that can turn what would normally be a multi-phase scheme into a single atomic transaction, such as releasing coins on many chains all at once as part of an escrow. And so I'm running out of time, but when you can trust a contract to construct transactions for you, even if it doesn't sign them, which you can't do on Ethereum or any other transparent chain at the moment, unless you host and you trust your local full node, you can push a lot of the logic into the smart contracts. So logic around how to interact with the app and how to interface with it, or how the contract can interface with other apps. But because we have end-to-end encryption between yourself and the smart contract, you know that there's no person in the middle that can tamper with the results and say, if you ask the contract to construct a transaction that you're going to sign that will do a bunch of swaps, how do you know someone in the middle hasn't modified that to their benefit? And yeah, so I think the direction that I'm heading at the moment is intentions with composability and interoperability and simplicity, and trying to use the trust execution environment and confidential EVM to solve these problems. And thank you. That's all I have for today. Any questions? From this guy again.
So TLDR, please trust Intel, right?
If the NSA is not concerned about you, then you shouldn't be concerned about the NSA.
Or that's what they say.
Yes. Don't blow stuff up. Anybody else? Or we're done? Okay, thanks, guys.
Nice job, Harry.